Mechanically, the engine powering a fast-response industrial site is a jet engine. Strip away the aircraft nacelle and mount that hot core to a steel skid, and you have the aeroderivative gas turbine. Instead of flying at 30,000 feet, this aviation core is bolted to a concrete pad inside a steel enclosure, where it spends its life spinning a heavy electrical generator. A traditional piston engine breathes in pulses. Intake, compression, fire, and exhaust happen in a repeating intermittent sequence. A gas turbine runs on the Brayton cycle, a thermodynamic process where every stage occurs continuously. This animation shows the continuous flow. Air is sucked into the intake, squeezed in the compressor, ignited with fuel in the combustor, and blasted through the turbine blades to create rotation. Because these 4 stages, suck, squeeze, bang, and blow, happen simultaneously in different sections, the engine produces steady, smooth power rather than the pulsing torque of a reciprocating engine. Heavy-frame industrial turbines built for baseload grids can weigh hundreds of tons. This aeroderivative design trades that raw mass for a 30-to-1 compression ratio, making it the standard for naval applications and mobile power units where space is at a premium. You find these units on offshore platforms, where 30 megawatts of power must be squeezed into a package light enough to be craned onto a platform deck. Safely harnessing 10,000 RPM of continuous aviation power requires moving away from traditional mechanical intuition. Operating this machine is a matter of absolute precision in the management of its auxiliary lifelines. There is no physical metal shaft connecting the engine's hot core to the power generator. They are mechanical strangers, even as they work in unison to produce electricity. The engine is built as 2 independent rotating systems. The first is the gas generator. Its singular purpose is to ingest air, burn fuel, and produce a high-velocity stream of hot gas. The second system is the power turbine. It is aerodynamically coupled to the gas generator, meaning the expanding exhaust gas, rather than a solid metal shaft, is what physically spins the turbine blades. This separation allows for a critical operational advantage. The power turbine can stay locked at a rock-steady 3,600 RPM to match the electrical grid frequency, while the gas generator core fluctuates up and down past 10,000 RPM to meet changing power demands. A single shaft design would require a massive, complex speed-reducing gearbox to force the core's high-speed rotation down to the generator's synchronous limit. By transferring power through gas rather than metal, the engine maintains perfect electrical synchronicity without exposing its internal components to the mechanical stress of variable speed coupling. You cannot bump start an engine this large. Before combustion can begin, the compressor must already be moving fast enough to establish a massive, controlled airflow. The hydraulic starting system uses extreme fluid pressure to drive a starter motor. This motor applies the initial torque required to crank the rotor up to a self-sustaining speed before any fuel is introduced. The starter uses a one-way clutch that automatically disengages once the gas generator hits roughly 4,500 RPM. This ensures the starter isn't dragged along and destroyed as the engine begins to accelerate under its own power. Once the igniter spark and fuel flows, the system monitors the exhaust temperature. If a rapid temperature rise isn't detected within a strict 10-second window, the start sequence aborts automatically. This abort is a critical safety measure. Pumping unburned fuel into a hot, pressurized combustor without a confirmed flame creates a severe explosive risk if ignition happens late. The engine is designed with a dual-fuel manifold, but it cannot run on a blend of both. Operating procedures strictly prohibit mixing natural gas and liquid fuels during a single run. When running on the coking trap, on shutdown, the manifold must be completely drained. If diesel remains in the hot nozzles, the residual engine heat bakes the fuel into hard carbon deposits that permanently clog the spray orifices. Precision timing during the start sequence and absolute drainage on shutdown are the primary defenses against fuel system failure or permanent nozzle damage. The extremes of this machine require 2 entirely separate lubrication circuits. A single oil type cannot satisfy the heat of the turbine and the weight of the generator simultaneously. The gold path represents the turbine lube oil, a high-performance synthetic ester designed for 10,000 RPM and extreme heat. The blue path is the generator lube oil, a standard mineral oil used for the slower, cooler sleeve bearings of the generator. Engineers must keep the synthetic oil contained within a bearing housing that sits inches away from a 1,000-degree gas path. If the oil weeps past the seals, it creates an internal fire risk. Sump pressurization solves this by bleeding high-pressure air from the compressor to create a wall of air against the bearing seals. This air pressure is kept slightly higher than the internal sump pressure, forcing any leakage inward rather than letting oil escape. Consider the consequences of a total plant AC power blackout while the massive generator is spinning at 3,600 RPM. In a blackout, the auxiliary lube pumps die instantly. Without intervention, a coasting rotor weighing several tons would score its own bearings and seize within seconds. To prevent this, the package includes overhead rundown tanks. These use pure gravity to dump stored oil into the bearings, ensuring the rotor stays lubricated until it reaches a full stop. At full load, active pneumatic pressure and high-temperature synthetic chemistry maintain the engine's internal boundaries. But in a total systemic collapse, gravity is the only failsafe that protects the machine. A turbine is in its most mechanically vulnerable state in the minutes immediately following a high-power shutdown. This cross-section shows a thermal mismatch. The thin outer casing loses heat quickly and begins to shrink. The massive, dense rotor spinning inside retains its heat and its physical expansion much longer. As the casing cools and constricts, it shrinks around the still expanded rotor. The clearance between the turbine blade tips and the casing wall effectively disappears. If an operator attempts to restart the engine during this window, the centrifugal force will grind the expanded rotor blades directly into the shrunken casing, causing a catastrophic rotor rub. When the coasting rotor drops a low 300 RPM, the control system starts a 10-minute countdown clock. To restart safely, operators must initiate a 5-minute motoring cycle before the timer expires. This uses the starter to force cool air through the core, restabilizing the internal clearances. If that 10-minute window is missed, the system enforces a hard 4-hour lockout. This forces the unit to sit idle until the rotor and casing cool down and equalize naturally. There is a secondary risk even when the engine is off: windmilling. Unpowered external airflow through the exhaust stack can keep the shaft spinning for days. Windmilling between 100 and 1,000 RPM for more than 5 minutes is lethal to the machine. Because the lube pump is driven by the shaft, it cannot provide adequate oil at those speeds, and the dry friction destroys the bearings. 0 RPM is not a signal of safety. The invisible thermal momentum and residual airflow will destroy the asset if field engineers ignore the cooling requirements. Maintaining an aeroderivative turbine requires moving away from fixed calendar-based overhaul schedules. The program runs on on-condition maintenance. Major service is triggered solely by direct physical and diagnostic evidence. This evidence-based system uses a 3-tier hierarchy: Level 1 for on-site visual fixes, Level 2 for modular section rebuilds, and Level 3 for complete restoration in an authorized test cell. Gathering that evidence requires laboratory-grade fluid analysis. Because of their tighter clearances, turbine bearings are held to a much stricter particle count standard than the generator bearings. Contamination invisible to the eye can lead to premature failure. Technicians gather mechanical evidence using borescope cameras to inspect the hot section without teardown. Every crack or dent found on a blade is measured against a specific tolerance bar. If the defect size exceeds the limit, the component is flagged for immediate modular replacement. Environmental monitoring is equally rigorous. Combustible gas sensors protect the enclosure from invisible leaks, but they drift over time as filters accumulate dust. Calibration requires a strict sequence, confirming a 0 reading in clean air, then applying a known test gas to set the span. If this process takes longer than 12 minutes, the system aborts and reverts to its previous calibration to prevent a life safety monitor from being left in an unverified state. A field engineer's primary responsibility is enforcing the strict physical, thermal, and chemical boundaries required to safely harness an aviation core on the ground. Responsibility for the machine begins with respecting the data.